So, in our last video, we have observed, or rather, we have studied a few like properties of power equivalent circuit. Well, so it was like here we are having R naught here one fictitious resistance. Right. So this is V1. Here it is I1. This is E1. R naught Jx naught. Actually, this is if we put it, this is minus E1, and this was I2 dash. This is I naught, and this side it was your E2 dash. Well, so if that is the case, then what we can write is that okay, so this one is mechanical analog of power electrical machine with our induction machine load, electrical analog of the load connected with our induction machine terminal. And in my last video I have explained that how the motor can understand that some load is applied across it, some load is applied on its shaft. Now we'll see the power flow diagram of this machine, and also this one, that see one thing, yeah, okay, now it is at this moment it's not that much important. I'll draw the approximate equivalent circuit later, but here what we can do is that we can like yes, here we can write it like so. What is your input power? Input power is this theta 1 is the input power factor angle, right? Now first what is the drop you should subtract is that energy stored in magnetic circuit or magnetic reservoir, that is how much? Pi minus 3 I square R1, I1 square R1. This is the amount, means this is our stator copper loss. So this much power is going to core. Now from this we need to subtract the so this gives us that it is very important term, that is air gap power. So this air gap power, now interestingly, we have already discussed that our induction machine behaves like a secondary short circuited transformer, where the secondary side resistance is a variable resistance. So if you may refer to this diagram also. Now from this what you can see that this power, what is the power here? This power is our air gap power. Like here the power is air gap power. Here it was Pi, then I subtracted 3I1 square R1, then I subtracted this PH plus E, then I get this air gap power. Now it is clear that if you consider the secondary side or the rotor side comprises only one element that can consume power, and that is 2 by S. Means if you just add these two together, you will get R2 dash by S. So in other words, what we can write is that air gap power, just a minute, air gap power is equal to 3 I2 dash square R2 dash by S. Do note here I am taking I2 dash square, so whether I2 dash is it is irrespective of the direction of I2 dash. Now that is the case, that then what is your power available to your shaft? Power available to your shaft will be sometimes it is defined as PG. So this PG minus rotor copper loss gives us our shaft power. So PG minus 3 I2 dash square R2 dash is equal to our shaft power. Now you may raise a question that, sir, as you have said, the rotor circuit can have a different number of phases. When a rotor, it is not necessary for the rotor to have 3 phase. It can have 5 phase, 7 phase, 6 phase, 2 phase, any phase. So how you are saying this? For understanding this, I have already mentioned that this whole thing is rotor equivalent referred to stator. So
it was from our equivalent circuit per phase to just three phase conversion. So if we have a per phase circuit, means a single phase equivalent circuit having rotor resistance R2 dash referred to per phase, then I am just means this again and again I am telling you, this equivalent circuit whatever I have drawn, this is only with respect to stator side. It is not possible for me to figure it out from the rotor side, because rotor is a mechanical part. So mechanical way you will get a mechanical analog, but if we are wanting an electrical analog, and that is why we have to figure it out from our input side. And input side, it is that whole thing, this whole circuit is referred to a single phase equivalent of the three phase circuit that is seen by the input source, right? So whatever this input source can see a single phase equivalent of this whole machine, this is the structure. Now if what would be the scenario if you consider in terms of three phase, you need to just multiply everything by 3. So even if your rotor is having 5 phase, you can multiply it by 3. Okay, so I hope you get my point. Now there is another thing that we should not forget, that this shaft power can be written like this is 3I2 dash square R2 dash by S minus 3, this is becoming what, 3I2 dash square R2 dash. Therefore the shaft power is what? Shaft power is 3I2 dash square R2 dash by S 1 minus S. So shaft power is equal to PG into this much is our air gap power. So this is air gap power into 1 minus S. Anyway, if you still have confusion with this formula, you can see there are many teachers available there online who will explain you all these things, and their modacity is quite good. They can make you means they are good at means writing these formulas. Obviously they I can bet, and means I'm not here to means like publicizing my own understanding in electrical machine, but you will find many videos on induction machine with all these formulas, but no one will explain that how even if we have 5 phase induction machine rotor, we can write the rotor loss as 3I2 dash square R2 dash. Anyway, people are having their choices, and the choices have their consequences. Now with this here, if you ask me to write the equation, you can write it like in terms of equivalent circuit, that okay. Now let us consider the torque developed. So what is the amount of developed torque? Torque developed is equal to what? It is equal to Pm by omega r. What is omega r? That is in speed in radian per second. Means nr was in rpm, omega r is in radian per second. Now this Pm is what? This Pm, if we consider it is the shaft, means actually this is not shaft power. We can say that
gross mechanical power. Here it is also gross mechanical power. So this, once you, if your friction and windage loss is mentioned, so if you subtract, the output power will be this gross mechanical power minus your constant mechanical losses. And here is one nice argument is there, like we are considering that quite often what we do is that we do not consider this loss here. Instead of considering this constant mechanical loss here, we just do a little bit of means alternation, we do a little bit of manipulation with this power loss sequence. If you are getting confused, let me write once again for your information what I am trying to mention by this, the what power loss sequence is that here it is your input. Let me draw the circuit, then it will also make you clear to you. And this is also E2 dash. This is I2 dash. This one is I1. This is I0. Well, so here this is our input. Pi is equal to 3V1 I1 cos theta 1. Here it is the power loss, that is 3 I1 square R1. Then here we are having our PH plus E. Now if you just investigate this PH plus E term deeply, here you will find two losses. One is loss in stator core loss, another one is rotor core loss. Now then we subtract our rotor copper loss. We get this as gross mechanical power. So what is suggested that if we subtract that mechanical loss from this gross mechanical power, we will get net shaft power. So this mechanical loss should be subtracted at the end once your electrical energy is converted in mechanical energy. However, what I am telling you that let us keep or let us bring this mechanical loss here, where means in addition to this PH plus E, let us make it mechanical loss plus pH plus E, and let us term it as something that is constant loss. What is the significance of considering it as constant loss? See, as I have mentioned, it is stator core loss and rotor core loss. Now, rotor core loss is subjected to rotor frequency, that is SF, and your uh, like your voltage. Now, that when the machine rotate at a high speed, then rotor, although means you can argue that rotor flux remains same, but even and these losses are quite means proportional to flux density. These losses are proportional to means flux density, and if we vary both voltage and frequency, then the flux density should remain constant. But for a level of voltage that is quite below the normal voltage and a frequency that is also very small in compared to normal routine frequency, what we will have our losses can show, means if we means discuss our magnetic material property in detail, we will see that the losses will be small for rotor in running condition. Like more and more S approach towards zero, that is more and more the machine speeds up and reaching near synchronous speed, that the losses, or better to say core losses of rotor will decrease. And there is another thing, that is this change in core loss of rotor. However, when the machine speeds up, there will be a change in a proportional change. Your mechanical loss will increase. So, if we combine them, like rotor core loss is high when S is close to 1, but rotor mechanical loss is small when S is close to 1, but rotor mechanical loss is becoming high when the rotor speed is also high and S is close to 0. But for this S close to 0, rotor frequency become very small, and thereby rotor core loss become very small. So now if we add stator loss, rotor loss, means stator core loss, rotor core loss and mechanical losses together, then we can see that for slip these two losses, rotor core loss and these mechanical losses, they are like providing a kind of vernier action, means they are means doing a kind of maintaining, they are taking a responsibility of maintaining a constant loss. Stator core loss you cannot vary because it is dependent on your input side voltage and frequency. So what you will have here, that is pretty interesting, your losses will remain constant. So if you subtract that power here, there will not be any kind of, and instead of considering it as gross mechanical power, if you consider all these losses here, you will get the output mechanical power. That means net shaft power will be available to you here only. Now with this, what you can write is that your torque is equal to what? Torque is equal to shaft power by rotor speed. So it is Pm by omega r. Now what is Pm by omega r? That is equal to air gap power Pg into 1 minus s, and this omega r is equal to what? Omega s by 1 into 1 minus s. So that gives us Pg by omega s. This is a very important relation. Obviously you will get this important relation available in all the YouTube videos and explained by all the bodacious YouTuber and good YouTube teachers. So basically it is air gap power by the synchronous Actually, you may think that SAD is having SAD is like envy of their achievement. It's not like that, but sometimes people ask me question beyond class hours. They refer those videos, and those videos are containing so much erroneous information and faulty interpretation that it takes me means it takes a huge time, consumes a huge time from my own life just to debunk those like logically incorrect things. Just to debunk those facts, it takes a huge amount of energy and time from my own schedule. So that is why I am a bit annoyed with them, because they are getting popularity and I am getting affected because of their incorrect information. Anyway, now this is one expression of torque. What is the another expression of torque? Another expression of torque is that so while we will try to find out another expression of torque, what I would like to do is that I would like to take shelter of simple approximation. I will try to highlight the fact that even in most in the worst condition, the flux area is 92% of its no load flux or unaffected flux. So this branch can be taken here. So I would like to go for an approximate equivalent circuit like this. Because this is those who are following Chapman is a popular reference book. In my opinion, it's not a good book, but it's a popular reference book. So it is my duty as an instructor of this subject to make you aware that the book you are going to use
has its pros and cons. Like if you follow Chapman, then whatever the torque expression you will get, it is pretty complicated. And in your Indian exam, mm, all the problems, not most of them, rather all of the problems can be solved using this approximate equivalent circuit of induction motor that comes based on the assumption that even in the worst condition, flux variation is means flux, mutual flux cannot fall below 92% of unaffected mutual flux, and that is what allows us to bring this magnetizing branch ahead of series branch. If you follow Chapman, he will present an argument that you cannot bring it because there is no load current, is that. But if you keep it here, like in exact equivalent circuit, your torque formula, what is normally available in most of the books like your Theresia and other books, you will get the incorrect. Means there will be mismatch. And please don't go for a duel between Theresia and Chapman. They means again and again I am telling you that here people sometimes cross me telling that, sir, you told us that synchronous generator is a generalized transformer, but we read induction machine is a generalized transformer. So who is correct? Whether you are correct or the book we read is correct. It is not like that kind of professional mixed martial art fight that one has to win the game, so he or she could be declared as winner. It is like both of us can exist, and it is the slightest difference in our perception that may lead to different conclusion. But what happens in the machine, that is quite different than this simplifying analysis. And but how to reach there? Obviously, what happens in exact machine, I explained you using 12 slot machine. When I first explained, I do not know how many of you watch those videos, but if you watch, you will find it's a 12 slot machine that I had considered to explain you the basic means pitch factor and other distribution, electrical winding distribution. But in reality, you can have a machine with at least say 600 slots, 720 slots. You can have slots like that. So, but if we start with 720 slots, then it will become very cumbersome and no one will understand anything. Either way, people are not getting anything, and but still they play the video for 5-6 minutes. And if we started with the most real-time thing, then people will play it only for 10 seconds or 5 seconds just to see that the degree of complexity is there in the video, and then they will run app. So without going to that tassel and turmoil, here it is the approximate equivalent circuit. Again, I am telling you, if you are following books like Theresia and other books, you will get this. If you follow Chapman, Chapman will argue not to bring it here, but both of them are correct. So if we bring it here, this approximate equivalent circuit, then we can write I2 dash is equal to what? Equal to V1 by root under R1 plus R2 dash by E square
1 plus x2 dash square. Now that lead us, because your torque is what? Torque is Pg by omega s, and what is your Pg? Your Pg is 3 I2 dash square R2 dash s omega s. So this gives us 3 V1 square R2 dash by s divided by R1 plus R2 dash by s whole square plus x1 plus x2 dash whole square whole into omega s. Now this is the torque in Newton meter. However, you can have this torque in or sometimes you can replace this omega s, like if it is given in rpm, then it will be 2 pi ns by 60. But another form is available, that is the torque in synchronous watt. Synchronous watt is nothing but the expression of power. It is like whatever is your air gap power, that is known as the torque in synchronous watt. Because if you consider the expression of torque, you will see that torque is proportional to where I have written, torque is air gap power by synchronous speed, and synchronous speed is something that is like dependent on your stator structure and input frequency. So as long as you are having a fixed stator structure and fixed input frequency, your synchronous speed will remain constant. So for sake of simplicity, we can consider it constant, and then we can represent this whole torque. Means the actual torque is just getting scaled by the air gap power scaled or divided by this synchronous speed, 1 upon synchronous speed. So if we do not do this scaling for our ease of representation, then we will get our torque in synchronous watt. Basically that is the air gap power. So now based on this, but again this formula we get by considering the approximation of bringing this magnetic circuit here. Just a minute. With this expression, what if we take them term by term, what we will get is that this torque is so only one thing that is variable in this expression is this s, and its presence both in numerator and in denominator. And also interestingly, the presence of s, like in many books you will get the shape of the torque speed characteristics. But interestingly, we must understand that why it looks like that kind of samosa. Yeah, it's kind of means when I went
in 2007 when I went there in facing an interview at Bhabha Atomic Research Institute. So my interview was good, but because I drawn that diagram that was kind of rather the diagram I drew was somewhat pointed, having pointed shape, and it was a bit steep than what it should be. The curve is very having instead of smooth end, it was having pointed sharp end and discontinuities. So that was the term they used to mock my drawing skill. But anyway, though they were good people and even they tried to grill me and grind me like anything, but somehow I succeeded to convince them with my level of knowledge, and they were also pretty happy. But they were like, it is means the diagram I drew for them it was like a samosa because it was somewhat pointed. Anyway, so it's long back. Good old days. Now here it is like if we see this expression here, you can see that it is appearing in numerator and denominator. Now, in order to understand the top slip characteristics shape, the shape is available in many books. I am not going to draw another samosa once again, but rather I would like to explain that whether it's a pointed samosa or a smooth cornered round shaped object, why it takes this typical shape. Okay, let me just insert one such kind of samosa here. Yes, so this is the diagram of such. Here you can see bunch of samosas are here. Like if we think about this, then let me pick up one particular samosa to make you understand what it was. And in any book like Thereja, Bhimra, and Nagrat Kothari, then your YouTube channels and other videos, you will get carved like this. But only a few people will make you understand that why we are getting this kind of curve. And interestingly, more we take value of r to small, we'll have a curve, squished curve. Like the curve will give us these points are the points of maximum torque. This diagram I have taken from the book of M.G. Say. So this is, you can see that all these are the points of maximum torque. So this is getting squished for small value of R2. However, for a particular value of R2, as I have marked this diagram with red color, one particular curve for a fixed R2, let us try to understand how this kind of typical shape is coming and what is that particular value of slip which offers us the maximum torque. Rather, once we can so before we explain this peculiar shape of this torque speed curve, I would like to do one thing, that is I would like to find out the expression of maximum torque. And in order to do so, we can do one simple manipulation, is that
instead of dealing or rather dwelling with this R2 dash by S, let us replace it by RL. And instead of finding out it in terms of dTds, means we have to make dTds is equal to 0, and that will give us that the value of S for which we are having maximum torque. So what we do, it instead of doing dTds is equal to 0, we do ddt RL is equal to 0. So here that one will become the modified torque expression in terms of RL will be 3V1 square RL divided by R1 plus RL whole square plus X whole square, where X is equal to X1 plus your X2, right? So now our objective is to solve this equation for dTdRL is equal to 0 and then find out the value of RL. If you do it, you will get the value of RL will be coming around that means your R2 dash by S will be this is an important formula. Right. Now this one is an important formula, and the value of maximum torque using this formula of RL, you will see that T max will be your by 2 into so clearly you can see here that one interesting thing is that T max is independent of R2 dash. So and SMT we are getting for a particular value of R2 dash. So obviously see this SMT is the point. If we go this one, the SMT is that very point. Here is this point is our, at this point our slip is SMT, and if we see the expression of this SMT, it is getting a ratio of R2 dash with the remaining circuit parameters. So if you increase R2 dash, obviously this SMT will increase. See, this is the value of slip. Here the value of slip S is equal to 0. Here the value of slip S is equal to 1. So okay, let me just
minimize this to a certain extent. Yeah. Now you can see that here s is equal to 0, here s is equal to 1. So if you make R2 dash large, that will shift SMT in this direction. Well, that's great. Now think about this particular value. This is our SMT for which we are having, but what happens when it is within 0 to this SMT? In this 0 to SMT, if you see this expression, this R2 dash by S, SMT being lesser than this R2 dash by this whole thing, until unless your S means in this region what you are having, your S is less than this value. So if S is less than this value, then what you are having here, you are having this whole thing is like the slip. Means try to understand this one clearly. Once this is SMT, we are getting this inflection point, but before that it is like if you take R2 dash by S, this ratio will be greater than like 1, and that this R2 dash by S not only greater than by 1, the variation with that slip is linear. So once you increase slip S, that R2 dash by S will also increase. Why? Because try to understand this. Here means when it is less than SMT, that means the denominator is less than R2 dash. Now when you are putting it here, then basically what you are getting something that is linearly proportional with slip, because in your numerator you are having 1 by S, in denominator you are having by S square. So in this region obviously the curve will vary in a linear manner, and once you exceed SMT, then it will follow the equation that is y is equal to 1 by x. Before this point it is almost y is equal to x or y is equal to mx that is governed or that is a linear equation, and in this region it is almost like a hyperbolic region, right? So this is why we get this kind of samosa type of structure, and this is the value of maximum torque. One thing that is interesting to note from this diagram is that maximum torque expression is independent of rotor resistance. So how can we explain it physically? Physically, rotor maximum torque or torque that is dependent on your air gap power, and it's a ratio between air gap power and synchronous speed. Now air gap power and synchronous speed has nothing to do with your rotor resistance. Obviously you can argue that if rotor resistance is small, then it can absorb more air gap power or can means instigate flow of more air gap power. But in other way, the air gap power is something that is just difference between your stator means input minus core losses minus stator copper losses. So from that perspective, your air gap power has nothing to do with your rotor resistance. right? So if and the change in rotor resistance, like you may argue that rotor resistance, higher value of rotor resistance can reduce the current and thereby the reduction in air gap power. Do understand that there is another factor x2, and actually x2, the leakage is proportional to the frequency. So higher value of R2 and X2, they are like, it cannot be means they are independent of each other. So it is obvious that torque, that one is independent of your maximum torque, is independent of your rotor resistance, because that is only governed by the stator side. Now, and that is also logical, because see, how much maximum torque means what? That is maximum PG by omega s. So it is obvious, it is something that is relating your maximum value of how much input you can observe for a machine. So this maximum value obviously should be governed by the input side data, not something that is dependent on your output rate. Now if you consider the starting torque, however, at starting what is happening here, your S will be 1 and starting torque is directly proportional to rotor resistance, because R2 dash is appearing in your numerator part. Now again you may argue that R2 dash is in numerator and R2 dash is in denominator. So if we are having higher value of R2 dash, then how we can claim that that will actually going to give us a higher value of starting torque? So I leave you with this question and you please try to find out the answer. The question is very simple. For S is equal to 1, we say that starting torque is proportional to R2 dash. Now whether this is a generalized statement, if yes, then it also implies an open circuit condition, like if you break the entry and keep your rotor circuit bar open, then you will have infinite R2 dash and therefore you will have infinite starting torque. But physically your machine will not start. Like if you do not have any closed circuit in your rotor, then there will be no flow of current through the rotor circuit and there will be no torque. But means this expression seemingly indicate that it is going to give us an infinite value of starting torque if we keep the rotor circuit open. So where is the fallacy, that we will discuss in our next video. And if you apply your logical sense, you can also figure it out by yourself.